Welcome to another session of vector function. Today we will look at the continuity of vector valued functions. This is the third session in the series. Let's look at the definition of continuity of vector valued function. We say r of t is equal to f of t, g of t, and h of t is continuous at t is equal to a whenever the limit of r of t as t approaches a is equal to r of a. That is, whenever the limit and the value of the vector valued function are the same, we say the limit is continuous. The function is continuous at that particular point. Notice that in terms of the component of r, this will say that r of t is continuous at t is equal to a whenever the limit of f of t, g of t, h of t as t approaches a is equal to the value of the function at a, or otherwise f of a, g of a, and h of a. Let's look at an illustrative example. Let's assume that r of t is defined as t plus 1, 3t, then t plus 1, then t squared. Let's find whether the function is continuous at t is equal to 1. So this will imply we'll find the limit of r of t as t approaches 1. The limit of r of t as t approaches 1 will just be the limit of the individual functions as t approaches 1. So the first function is 3t. The first component function is 3t. So lim 3t as t approaches 1 will just be 3 into 1, and that will yield 3. And then the limit of t plus 1 as t approaches 1 will just be 1 plus 1, and that will yield 2. And then the limit of t squared, the last component function, as t approaches 1 will be 1. That is 1 squared, which is still 1. Then we'll find the value of the function r of t as the function of r, the value of the function r of t at t is equal to 1, and that will just be r of 1. And we know this can just be computed by just throwing 1 into the individual function. So that will be 3 into 1, comma 1 plus 1, then 1 squared. This is going to yield 3, 2, 1. So we can see that the limit and the value of the function at 1 are the same. The limit and the value of the function at 1 are the same. This is the same as this one. Okay. So whenever the limit of a function at a particular point is the same thing as the value of the limit at the same point. We see the function is continuous at that particular point. The next section, the next thing we shall look at is the range of continuity of a vector function. So let's look at the range of continuity, the range of values of t for which a vector function is continuous. Let's look at the first example. We have to determine for what values of t the vector valued function out of t, which is defined as e exponent 5t, then the length of t plus 1, and cos t is continuous. We should note that every function is continuous on its domain. So to find the continuity of this vector valued function, we look at range of values for which each of the individual component functions are continuous, and the net, or otherwise the intersection of all of them, will be the range for which the vector valued function is continuous. So we'll pick the component function one after the other. So the first one is 5 exponent 5t, e exponent 5t. We know this is defined on all real values of t, and as such, this is continuous on all real numbers. Then let's look at the length function. Length t plus 1 is continuous when t plus 1 is greater than 0. Remember, the length function is defined for numbers greater than 0. So for this to be defined, the value of t plus 1 should be greater than 0. And this will imply t should be greater than negative 1. This means anytime we throw in a number that is greater than negative 1, the value of t plus 1 will be greater than 0. Then let's look at the last one, cos t. Cos t is defined on all real numbers, and as such, it will be continuous on all real numbers. So the intersection of these three, since the first one is all real numbers and the last one is also all real numbers, the intersection of these three will just be this one, t greater than negative 1. So in fact, our r of t is continuous on the range t is greater than negative 1, which can be written as from negative 1, open at negative 1, to positive infinity. Let's look at the next one. The first component function is t plus 1 on t minus 1. And this is continuous on all real numbers except t is equal to 1. So it's continuous on all real numbers except t is equal to 1. Then t squared is continuous on all real numbers. Then 2t is so defined for all real numbers, so it will also be continuous on all real numbers. And in fact, since the last two are all real numbers And the first one is all real numbers except t is equal to 1. The intersection of these three will just be this one. So our r of t will be continuous on all real numbers. Continuous on all real numbers except t is equal to 1, which can be written as from negative infinity to 1 union 1 to positive infinity. Let's look at the next question. For this question, our vector function is defined as tan t absolute t plus 3 and then 1 over t minus 2. Tan t is a special case, so I'll deal with that later. So let's look at the last two, and then later on we'll look at the tan t. So the first one I'll look at is t plus 3, absolute t plus 3. We know this is continuous on all real numbers. Continuous on all real numbers. Then the next one is 1 over t minus 2. It's continuous on all real numbers except 2. On all real numbers. Real numbers except t is equal to 2. Now let's look at the tan. To be able to understand the range of values for which tan t is continuous, the best is to use the graph of tan t and see where there are breaks. Or better still, we can also use the identity for tan and look at and try to build a pattern from the identity. Then we can establish a general rule for which tan is defined or is continuous. We know that tan t from trigonometry can be expressed as sine t over cos t. So whenever cos t is 0, this fraction breaks down. So when cos t is 0, tan t is undefined. So let's look at what range of t or what numbers of t is cos t 0. We know the general one or the standard one, cos 90. We all know that cos 90 is 0. It is something that is always on the lips of students. Cos 90 is 0. Now the cos function ranges from 0, -1, and +1 for the multiples of 90 degrees. So for instance, the next multiple of 90 degrees is 180 degrees. Cos 180 will be -1. Then the next multiple of cos 90 degrees is 270. 270 degrees is 0. Oh, let me cross check. 270 degrees cos 270. Let's check with our calculator. Yeah, it's 0. Then the next one is 360. Cos 360 degrees. That is 1. Then the pattern continues in that order. Then the next one is cos 450. cos 450. Let's cross check that with our calculator. Cos 450 is 0. Then the next one, the next multiple of 90 is 540. Yeah, 540. So cos 540 degrees will be -1. You can cross check that with your calculator. Let's cross check and be sure. Yeah, -1. Good. So the cos function is always 0, -1, 0, 1, 0, -1, 0, 1 for all multiples of 90 degrees. At any point the cos is 0, tan is undefined due to what I've explained. So tan 90 is undefined. You can check with your calculator. Cos 270 is also undefined. Sorry, tan 270 is undefined. Tan 90 is undefined because the cos is 0. Then tan 270 is undefined because cos is 0 there. Then tan 450 is undefined because cos is also 0 there. We can write this expression in terms of pi. This is in degrees, take note. In terms of pi, these expressions will be cos pi over 2, and then this will be cos pi. The next one, cos 3 over 2 pi. Then the next one, cos 2 pi. This is cos 2 pi. 360, yeah, 2 pi. So this is for 360, this is for 270, this is for 180, and this is for 90 degrees. Remember, 180 degrees is pi radian. So you can use that relation to do the conversion. And then cos 450 is the same thing as 5 over 2 pi. And then cos 540 degrees that will be cos 3 pi. Cos 3 pi. So this is in radians. These angles are in radians. Good. Let's see whether we can build a pattern from the multiples of 90 degrees. Let's do that on the next screen. So we have 90. Let's assume this 90 times 1, which is 90. This 90 times 2, which is 180, which is 90 times 3, 270, 90 times 4, which is 360, 90 times 5, that gives us 540, no, 450, 450. Then 90 times 6, that gives us the 540, etc. We can continue on and on and on and on. So this is what gives us 0. So we know cos is 0 here, cos 90 is 0 here, and this was -1, and this is also 0. Cos 270 also gave us 0. Then this is 1. Then cos 450 also gave us 0. 0. If we look at it critically, the odd multiples, the odd multiples of 90. Let me call them odd multiples. It means when you multiply 90 by an odd number, let me just coin that expression, odd multiples of 90. Just to mean the multiples of 90 that are obtained by multiplying 90 by an odd number. We can see that those ones, the cos is always 0 and tan will be undefined. This implies that the next one times 90 times 7, the cos will also be what? 0. And the next one will be 90 times 9, cos will also be 0 and tan will be undefined. So we can generalize, right? And the general expression to represent these values, the odd multiples of 90. And the best expression to achieve that is 2n plus or minus 1. So this will give us the odd numbers times 90 degrees, where our n is 0 or 1 or 2, etc. So when we put in these numbers into the bracket, we see that the bracket will always yield an odd number, whether negative or positive. If it is odd in absolute terms, the cos will be 0. For example, when n is equal to 0, we are going to have negative 1 times 90 or 1 times 90. Negative 90 degrees, this will yield negative 90 degrees, and this also yields positive 90 degrees. The cos of negative 90 degrees is 0, so tan negative 90 is undefined, and the cos of positive 90 degrees is also 0, so it is also tan is also undefined at that point. When n is equal to 1, we are going to get either 3 times 90 degrees. Sorry, when it's minus, let's do the minus on the left side first. When n is equal to 1, we'll have 1 times 90 or 3 times 90. That's plus or minus. And all these are what will give us odd multiplier. Then when n is equal to 2, we are going to have 3 times 90 or 5 times 90. That is when we are using the plus. Let me indicate here we are using the minus, and here we are using the minus in this column, and then we are using plus in this column. Remember, the formula is plus or minus. Good. So you can try on and on with all the numbers of n. You can see that the multipliers will be odd numbers, and once they are odd numbers, as we have established in this pattern, the cos will be 0, and hence tan will be undefined at that given point. So we can now conclude and say that tan t is defined on all real numbers, except when t is equal to 2n plus 1 multiplied by pi on 2. The pi on 2 is the 90 degrees, but I want to state this one in radians, where our n is equal to 0, 1, 2, 3, etc. Sorry, this will be plus or minus 2. Sorry, 2n plus or minus 1. Good. So the net effect of our problem, remember, we have to find the range of values of which the function is continuous. We have established that of the absolute function to be all real numbers, and that of the t minus 1 over t minus 2 to be all real numbers except t is equal to 2. And now we have also established that of tan defined for all real numbers except t is equal to 2n plus 1 times pi over 2, where our n is equal to these numbers. So the combination effect, or the intersection of these three, will give us the range of values for which r of t is continuous. So we can now state that our r of t is continuous on all real numbers except t is equal to 2 or t is equal to 2n plus or minus 1 multiplying pi on 2, where our n is equal to 0, 1, 2, 3, etc. So that is that. Let's look at the next example. So these are a group of exercises we'll do to end the session. I'll do the first two, then you try the last one on your own. Let's look at the first one. Now we have established the range of values for which tan t is continuous. So we'll not waste time, we just write it. Tan t is continuous on all real numbers except t is equal to 2n plus or minus 1 multiplying pi over 2, where our n is equal to 0, 1, 2, 3, etc. Then sine t squared for this one is defined for all real numbers. Defined for all real numbers. So to be continuous on all real numbers. Continuous on all real numbers. Then the last one is cos t, which is also continuous on all real numbers. So the net effect, or otherwise the intersection of these three, will represent our continuity for r of t. So r of t will just be continuous on all real numbers except n is equal to t is equal to 2n plus or minus 1 times pi over 2. So continuous on all real numbers except t is equal to 2n plus or minus 1 multiplying pi on 2, where our n is equal to 0, 1, 2, 3, etc. Let's look at the next one. For cos t is continuous on all real numbers. Then the square root of t, the radical sign is defined for only 0 and positive integers, positive numbers, positive real numbers. So this is defined or continuous on the range t is greater or equal to 0. And then for sine t is continuous. Continuous on all real numbers. All real numbers. Good. Continuous on all real numbers. So the combination effect or the intersection of these three will just be this one. So our answer, the range of values for which r of t is continuous. R of t is continuous on the range t is greater or equal to 0. We can write this as square bracket 0 comma to positive infinity. Good. So you try the last one on your own. The last one on your own. So this is the end of this session. Thank you very much for watching. Don't forget to subscribe.